Good evening. Today we start the 8th chapter in our textbook, Gravitation. It's a very interesting chapter, and for those of you in the future who hope to do aerospace engineering, where you will be designing, manufacturing, and maintaining spacecraft, aircraft, satellites, rockets, and so on, this is going to be the base of the higher physics you will be learning in your branch of engineering. Legend tells us that an apple falling from a tree inspired Newton to put forward the universal law of gravitation, which he used to explain the motion of planets and their moons. This universal law of gravitation, which is put forward in the 17th century, states that every body in the universe attracts every other body with a force that is directly proportional to the product of the masses and inversely proportional to the square of the distance between them. That is, if you have two masses, let's say we have a mass m1 separated from a mass m2 with a distance r between them, mass m1 is going to be attracting m2 with a force F21, and m1 will be attracted by m2 with a force F12, such that the two forces are equal in magnitude but they are opposite in direction, and the magnitude of this force is proportional to the product of the two masses and inversely proportional to the square of the distance between them. So you will see that mass m1 is going to attract m2 with F21 and mass m2 is going to attract m1 with F12, but the two have the same magnitude given by this, but they are opposite in direction. They are an attractive force. Now, this proportionality constant, you may replace it with equality. The constant being called the gravitational constant is g m1 m2 by r square, where g, the value was determined 6.67 into 10 raised to minus 11 Newton meter square per kilogram square. This was determined, the value of g was experimentally determined by Sir Henry Cavendish. 1 century later, in the 18th century, he experimentally determined the value of g. Now you will see that this value of g being very small, actually the force exerted is also an extremely small force, gravitational force. For example, suppose let's say this you take as 1 kg, this also has 1 kg, separated by a distance of 1 meter. Then if you calculate the force between them, it has to be g is 6.67 into 10 raised to minus 11. Then m1 and m2 both we have taken as 1, and the distance also between them is 1 square. So you will see that the force exerted is such a small force between these two. So that is the gravitational force with which two bodies attract each other. It's always an attractive force. So this tells you that if you throw a body up, it has to come down to the earth simply because the earth exerts a gravitational force on the body. And the acceleration with which it falls is called the acceleration due to gravity, and we will be deriving an expression for that acceleration due to gravity. Now before that, so if you throw a ball up, you expect it to come down because the earth exerts a force on the ball. But the ball is also exerting a force on the earth, right, with the same magnitude. But you don't see the earth moving towards the ball. And that is simply because the force is the same, which means, let's say we have this earth and we have a ball here whose mass is, let's say, mass of the ball, and this is mass of the earth. Okay. So force exerted by the earth on the ball and force exerted by the ball on the earth, both are the same. So force exerted by the earth on the ball, that is force exerted on the ball, will be m into b into ab, meaning mass into acceleration being force, equal to mass of the earth into acceleration of the earth, which tells you that mass of the ball by mass of the earth is acceleration of the earth by acceleration of the ball, inverse proportion. Let's take this to be 6 kilogram. Okay, so this will be acceleration of the mass of the ball is, we've taken it, mass of some body, not a ball, a huge body, 6 kilogram, divided by mass of the earth, is 6 into 10 raised to 24 kilogram. So this is 6 into 10 raised to 24 kilogram, which tells you that this ratio is 6 10 raised to minus 24, which tells you that the acceleration of the earth is 10 raised to minus 24 times acceleration of the ball, or acceleration of the earth is 10 raised to 24 times lesser than the acceleration of the ball. So you will see that the acceleration of the ball is really large, whereas the acceleration of the earth is only 10 raised to 24 times lesser than the acceleration of the ball, because of which you feel the ball moves towards the earth and the earth does not move towards the negligible acceleration. Okay, we are now going to derive an expression for this acceleration due to gravity, small g, which you already know for earth is 9.8 meter per second square. Now for that, we consider the earth of mass m and radius r. So we have the earth of radius r, capital R, and the mass of the earth we take as m. Let's consider a small body of mass m on the surface of the earth, negligible radius. Okay, so if I'm going to talk about the force acting on this body, force is mass into acceleration, and this acceleration is what we call as the acceleration due to gravity, the acceleration towards the earth. So let that be first equation. From the universal law of gravitation, we know this F is equal to g m1 m2 by r square, where this m1 is the mass of the earth, m2 is the mass of the body, divided by the distance between the two centers. This radius being negligible, we will take this distance as r, and we have that as r square, equation 2. The left hand side is representing the force on the body, so I may equate m into g equal to g m by r square. Cancel this and we have an expression for g, which is capital G m by r square. So you substitute all the values. If you plug in the values of g as 6.67 into 10 raised to minus 11, the gravitational constant, which is the same for all bodies in the universe, mass of the earth as 6 into 10 raised to 24 kilogram, and the radius of the earth as 6,400 kilometer. You substitute all these values to get the g value as 9.8 meter per second square. So you should also know that this g is constant for a given planet. We have given the mass of the planet Earth and radius of the planet Earth, right? So if you go to the moon, you change the values of mass and radius of the moon and you will see that g is different. So small g is different for different bodies, different planets, moon and so on. But this capital G is a universal constant. Okay. We also need to consider whether g is a constant throughout, or let's say how does g vary as we go higher. Also we need to see how g varies as we go deeper into the deeper down into the earth. So first we are going to look at the value of g. How does g change as we go higher? So for that, let me write acceleration due to gravity at a height h. Okay, so we have the earth here at some height. We have the earth here at some height h. We've kept a body of mass m. This is capital M. We know that the radius of the earth is capital R, and from the surface of the earth I take this as h. Okay. Now at this point the acceleration due to gravity I'm going to call as gh. That means acceleration due to gravity at a height h. So now if I look at the force experienced by the mass m due to the earth, that's going to be F is equal to m into g, m into acceleration. At that point the acceleration is the acceleration at a height h, and that I take as my first equation. This is also equal to, by universal law of gravitation, g capital M small m divided by distance between this center and this center, going to be r plus h the whole square. That's my equation 2. So I may now equate the right hand sides and get this as gmm by r plus h the whole square. So I may cancel this and rewrite this as gm by, I'm going to take this r outside so that this becomes 1 plus h by r the whole square. Why I'm doing that is because if I get this gm by r square, I can replace it with g on the earth, because we just found out that small g on the earth is gm by r square. So I want to relate gh to g, that is why. So now I may write this as GH is equal to, on top I have this GM by, I'm going to open this, so this is R square, and then take this on top, that is 1 plus H by R the whole square, can be written as 1 plus H by R the whole raised to minus 2, because I've taken it up. This is what we have as G on the surface of the earth. Now, I can use this binomial theorem to expand this. Now, those of you who have not done math, binomial theorem may not be familiar to you, but in physics, it's very simple because we neglect the higher powers of x. Let me tell you how. See, 1 plus x raised to minus n is 1 minus nx by 1 factorial plus, and there are other terms, the very next term being a square of x, and then the next term being cube of x, and so on. But we neglect all higher powers of x because, see, in our case, 1 plus x raised to minus n, this x is actually h by r, right? So x being h by r is very small because we are looking at a body at some height h from the surface of the earth. That height, if it is small compared to the large radius of the earth, then this h by r is a very small value. And if h by r is a very small value, that is x is small, then let's say for example 0.1. If you square 0.1, it's going to be 0.01. Cube it and you will have 0.001 and so on. So you will see that as the power of x goes on higher, it's becoming higher and higher, the value becomes negligible because h by r is small when h is small compared to r. So we are only looking at the first two terms. Okay, so we just need to use this equation. So those of you who have not done math, remember you can just substitute this equation there and this substitution here. So we have g at h here equal to this gm by r. I'm going to replace it with g on the surface of the earth, and I'm going to use this identity to expand this. So this is going to be, first term is 1 minus n is 2. So 2 into x is what? H by r. So this is h by r. So now I may write gh is equal to g minus 2gh by r, showing you that gh is less than g. So as we go higher, you see that the acceleration due to gravity is becoming lesser than g, lesser than 9.8. So it's 9.8 on the surface of the earth. You go higher and it becomes lesser than 9.8. That's what we see from this derivation. Next thing we are going to do is derive an expression for this acceleration due to gravity at a depth when you go into the surface of the earth, deeper down into the earth. That's what we're going to do next. For that, so this is acceleration due to gravity at a depth d. Okay. At a depth d from the surface of the earth. So let's look at the figure. So this is the earth whose total mass is m and radius is r. Now we go down into the surface of the earth to, let's say, a depth d. We place a mass of a body of mass m, and this let it be on a smaller mass. So this is where we have placed the mass. We have gone to a depth d here and placed this mass on an inner sphere whose mass is, I call as ms, mass of the smaller sphere, and its radius is natural. So this whole thing is r, right? So this is going to be r minus d because this whole thing is r, this much is d, so this has to be r minus d. So radius of the small sphere is r minus d. I hope that is clear to you. Okay. Now we'll derive. So this mass now experiences a force which is given by m into g at d, where at this point the acceleration due to gravity is what I am writing as g at d, meaning the acceleration due to gravity at a depth d from the surface of the earth I am denoting with g at suffix d. So that's my first equation. By universal law of gravitation, g into m1, m2. Now this small mass is on the surface of the mass ms. So the two masses m1 and m2 are going to be ms and m. So we may write ms into m by distance between the center of the two bodies in consideration, that is from here till here will be approximately r minus d. From here till here will be r minus d, and that is going to be r minus d the whole square, which is my equation 2. Now I may equate the right hand side and write m g at d equal to g ms m by r minus d the whole square, where I cancel this m and this m. Now I want to put this in terms of small g so that I can compare. So I want to change this ms into terms of mass of the earth m, that this mass of the earth m. So I may write, see, what is mass equal to? Volume into density, because you know density is mass by volume. So the mass of the small sphere here, the small sphere will be, volume is 4 by 3 pi. The radius of that small sphere is r minus d the whole cube into the density of that material, that sphere. Whereas mass of the earth will be, whole mass of the earth will be 4 by 3 pi, radius of the earth is r cube, and the density is the same material. So from this I may write, ms by m is this 4 by 3 and this 4 by 3 pi will get cancelled. Density here cancelled. So r minus d the whole cube by r cube. So I can get an expression for ms by simply bringing m to the right hand side. That's what I'm going to do here. So g at d is equal to g into this ms I can write as m into r minus d the whole cube divided by, there's an r cube here which I'll split and write as r square into r, that is r cube, and then there's an r minus d the whole square here. Why I did that is, we know that this gm by r square is small g on the surface of the earth. So now we may write this as g at d is equal to, this I replace with g, and here I have this whole thing getting cancelled. So we have r minus d by r, or g at d is equal to g into 1 minus d by r, or g at d is equal to g minus gd by r, showing you that gd is less than g. So again you arrive at the result that as you go down towards the core of the earth, from the surface of the earth as you go down, the acceleration due to gravity becomes lesser than 9.8 meter per second square, lesser than g. So what we found out is now g is 9.8 on the surface of the earth. Whether you go higher up or deeper down into the earth, the value of g becomes lesser than 9.8 meter per second square. We'll stop our session now and continue in our next class. Thank you.